In this video, I'm going to talk about standardization of rates, and this is one of the topics that I struggle with the most for some reason, so I'll do my best to describe it the best I can. So standardization is something you can do that allows two populations to be compared on a level playing field, and there's a lot of reasons that two populations might not be comparable. Just to kind of start with just the very foundation of standardization that we're all kind of familiar with. If we were just looking at the number of deaths in a year between a developed country and an undeveloped country, we'd see that there's a lot more deaths in this developed country. But what we haven't taken into account here is the size of the country. So if we're doing a mortality rate in 2002, so the number of deaths over the number of people, so we're able to get a denominator in there that takes into account the different size of these countries, we can get a very different picture. So that's kind of like the simplest, most intuitive way of standardizing, but it can get a little more complicated when the two populations don't just differ in size, but also differ in some confounding variable. So if we're looking at the relationship between the country you're in and mortality rate, there's a chance that this could be skewed by the age distribution of the country, where different countries have different age structures, which I'll show in a second. And age distribution is also related to how many people die in a year, because the older population might be more likely to die in some populations, and in others, maybe the infant mortality rate is really high, so this is something that could distort this relationship. So this is an example of a population structure for a developed country where the majority of people are in this age group, I guess the baby boomer age group, and we do have some old people, not that many, but significantly more than this undeveloped country where the bulk of the population structure is young in this country, and it's very rare to be old. So yeah, these are two countries that differ significantly in their age structure, and that might make mortality difficult to compare between the two. So there's two ways of standardization I'm going to talk about. In both cases, you have a study population or study populations and a standard. And in both cases, one of these populations is providing the stratum-specific rates, so the rates stratified by age, and the other is providing the distribution of some confounder. So direct standardization or external standardization uses an external standard. So let's just say we have two populations, like the developed country and the undeveloped country, that differ in their age structure. We could get a third population, and we could standardize the rates in these developed and undeveloped countries based on the confounder distribution in that standard population. So you're basically asking, would the crude overall rate differ if they had the same age distribution in this developed and undeveloped country? So we're basically forcing these two distributions to be similar by using a third distribution. We're basically taking the rates here and applying the distribution of this third standard in order to make the distribution in this developed and undeveloped country similar. And this will become more clear when I do my example. Indirect standardization or internal standardization, in this case, the standard population is providing the rates, and the study populations are providing the strata distribution. And it's typically used to compare one to another. So here there was three involved. There were two populations that we were standardizing, so meeting in the middle based on a third one. With this indirect method, it's internal because we'd basically be using one of the two, like the developed country, as the standard in order to put them, the undeveloped and the developed country, on a similar demographic structure scale. So I'm going to go over direct standardization first. So you start by stratifying your population by age, finding the age-specific mortality rates for each of the age strata, finding a standard population with an age structure you desire. So Typically, it's one it's hoping to be representative of everyone. So, like, if it's two different subdemographics coming from one city, like people who work in some job in Toronto versus some people that work in some other job in Toronto, you might use general aid structure in Toronto would be better. Would be what would be a good standard in that case. So the fourth step is finding the expected mortality rate in the developed country if it had the age structure of the standard population, and doing the same thing for the undeveloped country. And lastly, you compare the standardized mortality rate in the developed and undeveloped country, because now they're on a more level playing field where you've standardized the age distribution, so this confounder isn't influencing these measures when you're comparing them. So this is the way it looks more complicated than it is. It has more rows than I was hoping, but in order to make it realistic, I needed to cover all of these age ranges. But yeah, so we have these age strata separated into 10-year intervals. And for our developed and undeveloped country, we have the number of people in these strata, the number that died, and we can use that to find the incidence. Same with the undeveloped one. And we also have this standardized population, and the only information it contributes is the number of people in each strata. You'll notice here that it's these expected number of deaths here are for the developed and undeveloped country if they had this distribution of age. So hopefully that'll become clear as I go through the example. So this is data we would get from our study population. We'd go to this, or we'd find data on this developed and undeveloped country, and I guess we'd be following them for some specified amount of time, say a year. And I have it as like 50 here, but we could say maybe that's in like 50,000 or 500,000. This is just easier numbers to work with. So we have the number of people there's 50 people between the ages of 0 to 10, or 50,000, whatever it is. We have the number that died in that year, and same for the undeveloped country. So for each stratum, we can figure out the incidence. So one death over 50 people, we can figure out the incidence, and we can do that for everyone else. Now we have our standard population, and you'll notice that, like I was saying before, the problem with comparing this developed and undeveloped country is that they have a different structure of the number of people in each strata. So you can see already there's a lot of young people in this strata, but not a lot of old people, or sorry, a lot of young people in the undeveloped country, but not as many old people. And it's kind of switched for the developed country. I don't know how realistic that is, but it's just an example. And we're basically trying to put them on the same scale, basically by saying how would their crude difference differ if they both had 75 people in this strata and both had 75 people in this strata, basically, instead of having 150 in this one and 90 and 60 in this one. So like I said, the two groups have a different number of people. The two groups have a different incidence, and we're basically we understand that the incidence is going to differ between the two, but we want to set age constant, basically, or sorry, we want to set the number of people in the age strata constant. So we're basically forcing these two to be similar to this third standard structure. So to find the incidence is number of deaths over number of people. So we know if the incidence is 0.02, we can figure out how many deaths there should be if there is 75 people. That's how we get the expected number of deaths for the 0 to 10 age strata in the developed country. So we get 1.5. And we do the same thing for the undeveloped country. It has a rate of 0.1 in this strata. So if we have 75 people, how many deaths do we expect? We get 7.5. And basically, we can do that all the way through. We can do that all the way through and get numbers here. And so we have a total number of deaths. Just if we just were to collapse all of the strata, we basically have in the developed country, we have this observed number of deaths and observed number of people, and that gives us a crude incidence. Same with the undeveloped country. And we also have an expected number of deaths over this population structure. So basically we have this expected number of deaths. Incidence is number of deaths over the number of people. And now we have a number of deaths for the developed country divided by 529, and the number of deaths in the undeveloped country divided by 529. So basically we've standardized this, standardized the denominator. So like I said, the crude incidence can be found for each. You got 0.12 for the developed country, 0.23 for the undeveloped one. And we can also find the standardized incidence in the developed and undeveloped, where, like I said, it's the sum of the expected number of deaths in the developed and sum of the expected number of deaths in the undeveloped, divided by the same number, 529. So now we have a standardized incidence in the two groups that are more comparable. It would have been nice if I just made up this example. It would have been nice if I had one where the actual direction switched, like where the incidence went from being higher in one and switched when I did that. But basically you can see that they were more similar without being standardized and became less similar upon standardization. So this is a more realistic view of the incidence of death comparing these two populations when controlling for age. Another thing we could have done that some people might find more intuitive is, you'll remember here we had number of people in each age strata, but if we were to do the proportion of those age strata, then we'd get a weighting, basically. So there's 529 people in total, and we have 75 that are 0 to 10. So that gives us a weighting of 0.142, and we can multiply the incidence in the developed country by this weighting to get an expected incidence in this strata. So basically the amount of the total incidence being contributed by this strata. And we can do that all the way through, and you can see that you'll see what I mean when I said it's the amount of incidence contributed by this strata, because when you add them all up, it turns out being what we got in the previous example. You'll remember here we got 0.9 for the developed country and 0.37 for the undeveloped one. That's what we got here as well. So if you find this method more intuitive, then just do that one. So when you're choosing your standard population, there's some things that can go into it that might influence whether it's a good standard. So I'm going to talk about a situation where your choice of standard would matter. So basically, this is separate data. We're still doing developed and undeveloped, and we have age now stratified by under 30 and 30 and over. We have a rate for each of these strata, so this would be 40 over 200, 200 over 400, and same with the undeveloped one. To find the risk difference in this strata between developed and undeveloped, we would do the rate difference. It would be well, it's technically a risk because there's no time involved here, but yeah, it would be 0.2 minus 0.1, and the risk ratio would be 0.2 divided by 0.1. Okay, so you can see that depending on the age strata here, the risk difference is the same, while the relative risk differs depending on strata. So it's more of like an effect modification thing going on here, where the relationship between country and mortality differs in age strata, but it doesn't in the additive risk difference. So I'll show you the implications of that. So if we use a young standard, so this is our standard here. We have 1,000 people under 30 and 200 people over 30. So this is a young standard. We find our expected number in the developed country the same way we did before. So we take our rate in the people under 30 in the developed country, multiply by the number of people, and we can do that to get all of this information we need. So now we find the adjusted rate, and that's the expected number of deaths divided by the total number of people, and we can do that for both, and we get 0.25 and 0.15. And when we take the difference there, we get 0.1, and we take the fraction, ratio, 1.67. Now, if we have an old standard, so now we have 800 people under 30 and 400 over 30. Yeah, okay. We can go through the same calculation, and we find a risk difference of 0.1 and a relative risk of 1.5. So it'll help more if you see it all together. So when unstandardized, the risk difference was the same among the two age strata, and the relative risk was different. And when we use a young standard and an old standard, it didn't have an influence on the risk difference. The adjusted risk difference was equal regardless of what strata we used, but the relative risk depended on what strata we used. So what I'm getting at here is this would be a situation where you could really only compare these two populations with a risk difference. It wouldn't be appropriate to use a relative risk to compare them. And this could have been reversed. The risk difference could have been different depending on the standard we used, but the relative risk would have been the same. So this is something you'd need to look into to figure out what the best measure to compare the two populations would be, additive or multiplicative. So when choosing standard, there's a few ways you can go about it. You can use an artificial population where you just say 500 in every stratum. You can choose one of the two populations as the standard, or like I said before, you can use a representative third standard, like if it's two different occupations in Toronto, you can just use all of Toronto. So now I'm going to talk about indirect adjustment. For what I was talking about with direct, basically you're taking two study populations and comparing to a third standard. With indirect, with the two study populations, they're contributing the rates, and the standard is contributing the demographic structure. Indirect is reversed, so it's basically your stratum-specific rates are coming from a standard, and your demographic structure is coming from your population. And typically, it's internally standardized because you're just comparing two, and it would usually be like if I picked the developed country to be the standard and just standardize the undeveloped country based on the demographic structure of the developed one. So this will make more sense with an example. It's useful when we have stratum-specific rates missing, or we can use one of our two populations. So just to make this one faster and easier, age is just separated into two. I'm just doing under 40 and over 40. And in population A, we have 2,000 people that are under 40 and 1,000 that are over 40. And we have a number of deaths in each. And this is our standard population. We have basically the rate of mortality in these two strata. So we're basically asking here, would the overall mortality rate in these two populations differ if they shared they have the same age specific, we're just standardizing demographic structure like before, basically. The expected number of deaths in population A, you do that, to do that you find you multiply the number of people in that stratum by the rate in the standard population. So we get 200 expected deaths. We can do that with the over 40 as well to get 500 expected deaths in total. So the standardized mortality ratio, you can find that by doing the total observed deaths over the expected deaths in population A. So that would be 300 over... so there was... we observed 300, and that just got weird just because there's 300 here as well, but yeah, so we observed 300 deaths in that population, and we expect 500, so standardized mortality ratio of 0.6. Another thing we could have done, and mortality in A is lower than expected because we saw 300 and expect 500. Another thing we could have done is proportions again. So before we were finding the expected number of deaths, now we can find the expected rate. So if instead of having the number of people in these two age strata, we can do a proportion, and we can multiply across the same as we did before. And now to get the overall expected rate, we can just add the contribution to that total rate from each strata like before. And again, we can do the observed rate over expected rate. So we observed, that's 300 divided by 3,000. We observed a rate of 0.1. We expected a rate of 0.167. And again, it comes out to a standard mortality ratio of 0.6, just like we got before. And in order to go from this ratio to a standardized mortality rate for population A, yeah, and it's lower than expected like before, we can find the standardized mortality rate by taking that standardized mortality ratio and multiplying it by the rate in the standard. So if we're using different data than we did before. If we were using the developed and undeveloped country data, and let's just say we use the developed country as the standard, we'd use its crude rate basically. But let's just say, for the sake of our here, just that it's 0.2. That's the rate in the crude rate in this standard population. Let's say it's 0.2, halfway between. We can multiply our standardized mortality rate by that and get 0.12. And that's our standardized mortality rate in population A, while its crude rate was 0.1. And yeah, that lets us compare this. Lets us compare population A to the standard population on an even playing field.